Okay, here we go folks. This is the video of the questions that we worked through from the end of topic 5, and these are my work solutions. And here we have the question 1 with the graph. There's the graph there, and as we said for question 1, the key information is that the time constant is the resistance times the capacitance, but we don't have either of these values. So what we need to do is remember that the graph, the charging graph for the capacitor is Q equals Q max 1 minus E to the minus T over RC. That should really be a tau, but as I keep saying, so often typesetters just use a T instead of a tau. Q max, according to the graph, up here is 10 nanocoulombs. One time constant's worth of charging should take us to about 6.3 nanocoulombs. So go over to the graph, down to the time axis, and that should give you a time of about 45 seconds. So the time constant is 45 seconds. For question 2, again, it's a graph question. There it is there. We're given that the capacitance is 4,700 microfarads. We are given no other information other than what is on the graph. So what we need to do is remember that rule of thumb that approximately 5 time constants is when the capacitor is either fully charged if it's charging or fully discharged if it's discharging, and that to me looks like about 3.5 seconds on this graph. So 3.5 seconds fully discharged, therefore 5 time constants is 3.5 seconds, 1 time constant is 0.7 seconds, and then I have enough information to use my tau equals RC, T equals RC, 0.7 equals the resistance times the capacitance, which should give us about 150 ohms. This is the big long question, the deceptively short question in the PDFs or in the book. Here it is here. Just appears to be a very small question. If I just looked at that without reading it, I think I'm just doing a calculation, I'm getting a number, which I am, to be fair. However, it's quite an involved calculation. So the first thing that I've done here is note down the data that I'm given in the question to help me think. And it asks me to find the IRMS when F is 150 Hertz. So first thing I do is I work out using my XC equals 1 over 2 pi FC formula, the capacitive reactance for 50 Hertz. So 50 Hertz, 1 over 2 pi 50, value of the capacitor, gives me 5,488 ohms. Then the next thing I did, because I was pretty sure I was going to need it at some point in the question, is the capacitive reactance for 150 Hertz, 1 over 2 pi, 150, 580 times 10 to the minus 9 for the capacitance, gives me a capacitive reactance at 150 Hertz of 1,829 ohms. Then there's my impedance formula. This is the big version. R squared, and then the difference between XC and XL in the bracket there, squared, and then the whole thing square rooted. Now we don't have an XL, which is the inductive reactance. We haven't got to that yet, and we don't have one in this question, so that's just going to go away and give us a short form of this equation, which is this value squared plus that value squared, because there isn't anything to find a difference from. So 400 for the resistor squared, 5,488 for the capacitive reactance squared, add them together, square root it, and that gives us an impedance for this circuit of 5,502 ohms, which means I can then use VRMS equals IRMS, which it told us up here was 17 milliamps, times the impedance that I've just worked out, gives me a voltage supply of 93.5 ohms. Which then, since I'd already worked it out, I can now work out, I'd already worked out the capacitive reactance for 150 Hertz. So now I can work out the impedance for 150 Hertz, 1872, and then that gets me my RMS current at 150 Hertz, because my RMS voltage, it said in the question, was kept constant. I've worked out my impedance for 150 Hertz, 1872, so there I get my current for 150 Hz, 0.05 of an amp. Now, question 4, it was that rarest of things, an advanced higher multiple choice question. Well, there is what the options look like in my copy of the Scholar Notebook, which should look the same in your copy of the Scholar Notebook or the PDFs if you're using the PDFs. So we said it couldn't be A. Couldn't be A because that shows no variation at all between the frequency and the capacitive reactance. It couldn't be B or C because they both show an increase in capacitive reactance with frequency when we know perfectly well that it's an inverse proportion. So it's got to be D or E, and D is the one that shows the correct shape for that type of a relationship. So the answer has to be D. And then for number 5, easiest question in the entire set, we're given a 180 nanofarad capacitor, a 14 volt RMS supply. Remember, although the wording of the question here doesn't actually specify that it's an RMS supply, if they don't say it isn't an RMS supply, then it's an RMS supply. If the quoted value is an RMS value unless somebody somewhere says that it isn't. So we just pop the numbers in. XC equals 1 over 2 pi FC, 1 over 2 pi times 5,800 for the frequency, times 180 times 10 to the minus 9 for the capacitance, gives us a capacitive reactance of 152 ohms, which is what we were asked to work out. If we had been asked to work out the impedance, we would have to look at the question and see if there was a resistance or an inductive reactance to be brought into the equation, but there isn't in this case, so we just work out the capacitive reactance as asked, and that's that part done. And then part 2, given the RMS voltage and the capacitive reactance that we've just worked out, work out the RMS current. So VRMS over XC, 14 over 152, 0.09 amps. And that is that done. Now, as I said, if all of those 5 questions make sense to you, then pretty much anything that they could ask you in terms of working something out for an advanced higher question paper about capacitors, you are able to do. Give me a quick message on Teams or use the chat function if any of those 5 questions is not crystal clear by the time you've gone through them once or twice to check the details.